Hey all, so here's the example problem I worked through on Thursday, and I worked through it pretty quick, so I don't know if it made a whole lot of sense to you all. But so an amusement park ride, it's got a platform, and this platform rotates. It rotates 1.5 radians per second in the counterclockwise direction. And there's some car on the platform, car C, and this car rotates at 2 radians per second in the counterclockwise direction. The center of the car C is 3 meters from the center of the platform, point O. And the rider, let's use R instead of B. The rider R is 0.75 meters from the center of the car. I've got some animations to show you, but what'll happen, you've got this counterclockwise rotation in the car. It's moving just slightly faster than the platform itself. So what we'll see is some rotation that looks some feature that looks like this if we trace the rider as a function time. So both counterclockwise rotation in the car and a slower counterclockwise rotation for the platform. The question's asking find VB, what I called VB and AB here, but I mean VR and AR, the velocity and acceleration of the rider. I've done a couple of visualizations I'll show you in a sec. Well, maybe I'll show you right now. So here I've got it set up. I'll show you an animation of this, but I've got some stationary red axes, and they're symbolized by a capital letter Y and a capital letter X. And I've also got some blue axes that'll rotate. They're pinned stationary to the car, and they'll rotate relative to these stationary axes. So we can do a lot by using these rotating axes. So here's an animation I'll start, but what you'll see is the rider off to the right is going to rotate. I've set up a tracer for this thing to show you what's going on. So what we see is the rider, both the car and this center platform are rotating counterclockwise. And you can see the position of the rider as a function of time. This is characterizing this, so this is an animation of the motion. There's a relatively quick rotation of the car and a somewhat slower rotation of the platform, both in the counterclockwise direction. In this one now, I've pinned axes to both the car and the stationary axes to the platform. So blue are the moving axes, red are the stationary ones. And if I hit go, what I want you to pay attention to is the fact that the rider does not move relative to these blue axes. So I've pinned them to the rider as the rider goes around. So I'm going to hit play. There you go. So the red dot doesn't move relative to the x-axis in the blue, and the x and y-axes are both allowed to rotate. So this might help you out. One thing that we'll do is cross off a term that says that this red dot doesn't move relative to the x-axis. So keep that in mind as we simplify the problem. But I'll let it run for a second if you want to keep watching it. Now there's actually a couple of different ways to solve this. I'm going to call this case 1, and I'm going to show you case 2. Case 2 was the situation I was working in class, and I want you to try to work it both ways. In case 2, I've set it up. So both axes are coincident at the moment. So the blue, you can only see the blue axes, but the stationary red axes are in the same place behind the blue. And I'll show you this animation. But what's going to happen, the red dot, the rider's going to do the exact same thing, except instead of moving the blue axes like we've done on the left in case 1, instead of moving it with the center of the car in this location, I'm going to fix the blue axes to the center of this rotating platform. So all the blue axes are going to do is rotate relative to the position on here. And you'll note that the blue axes will stay pinned to the center of the car in this case. So here's that case when I run it. So keep an eye on the blue axes. There. So the blue axes, they're pinned to the center of the car and they're rotating through. And now note that there is some relative velocity of the rider to the blue axes. So this relative position, if I reset it, I'll show you. What I want you to pay attention to, and I run it again, is the fact that the red dot is going to move upward relative to the blue axis. It's going to move up, the rider's going to move up more quickly, and there's a term in there that we can't set to 0. You'll have to account for it when you work this problem, or if you follow the notes in class. But there is some relative velocity in this case of the rider compared to the blue axis. So, boom. The rider just moved upward more quickly than the blue axis. And what you want to figure out is the acceleration and the velocity right at time 0, right at that initial position. Here it is one more time if you want to see it. And just as a reminder, this is what we're going to analyze. Remember, in this case, case 1, the red dot doesn't move relative to the blue axis. So we're going to set it up a little bit different, and I'll work through this example for you. So here's a working equation you want to use in this case. I'll highlight it. And this term, this v, the velocity of r relative to c with this x, y, z notation, is the position of the rider relative to the blue axis. So because we've set it up such that the blue axes are rotating with the rider, we set that term equal to 0. This capital letter omega is the rate at which the blue axes rotate. So in this case, the rate at which they rotate, capital letter omega, is equal to the rate at which the platform itself rotates, 1.5 meters a second, plus the rate at which the car rotates. So the car rotates 2 radians per second counterclockwise, and the platform rotates at 1.5 radians per second counterclockwise. So the sum of those two is the rate at which these blue axes will rotate around the circle. In this term, v sub c is the rate at which the car is moving, the center of the car is moving. And initially, the center of the car is moving straight upward, and it's the velocity relative to the capital or the red xy axes. And the velocity of the car, 1.5 meters per second in the k hat direction, and crossed with 3 meters in the I hat direction. And we come up with a velocity of the car of 4.5 meters per second in the j hat direction. So we plug the velocity of the car in for this term, and what we come up with, the velocity of the rider is equal to 4.5 meters per second in the j hat direction, plus this capital letter omega, 3.5 radians per second. It's the rate at which these blue axes are rotating counterclockwise in the k hat direction, and we'll cross that with the position of r relative to c. So the position of r is just 0.75 meters to the right of c, or 0.75 meters in the I hat direction. Work through the cross product, add everything up, and we come up with a velocity of the rider, the initial velocity of 7.125 meters per second in the vertical direction. So the rider's going vertically, or going in the y direction initially. So we know the velocity of the rider initially, and now we want to figure out the acceleration of the rider by using this long equation. But the first thing to recognize is that we can cross off the acceleration of r relative to c in the blue axes, and we can do that simply because the blue axes rotate right with the rider. So the rider, this point, this dot, remember, doesn't move with the blue axes, so we can get rid of that. There is no acceleration, and there is no velocity relative to the blue axes. So here the remaining terms we need to figure out is the acceleration of the center of the car, and omega dot, which would be the rate at which the blue axes are accelerating. And they're not accelerating because omega is simply a constant. It's simply 4.5 meters per second. Or I'm sorry, 3.5 meters per second in the k hat direction. It's always rotating at that speed. So omega dot is equal to 0. So the acceleration of c, the acceleration of the car itself relative to the red axis, it's so it's the acceleration. We've got both acceleration in the normal direction towards the center of point O, and any acceleration in the vertical direction. So here's the normal component of acceleration, and any acceleration in the j hat direction. But as it turns out, this alpha, the rate at which the platform is rotating, is 0. So the rate at which the platform is accelerating, in the angular direction, or the angular acceleration of it is 0 because it's steady at 1.5 radians per second. So we know alpha is 0. Omega CO, like I said, is steady at 1.5 radians per second. So negative omega CO squared, and multiply that by the position of C relative to O, 3 meters in the I hat direction. And we come up with an acceleration in the negative direction. In the negative I hat direction, the acceleration is pointing straight towards O, right at the initial. The acceleration of C, is pointing straight towards O, the center of the car, at about negative 7 meters per second squared in the I hat direction. So we know that. Let's throw that into that part of the equation. So let's evaluate. We'll evaluate this cross product first. And omega, again, the rate at which the blue axes are rotating, 3.5 radians per second. We'll cross that with a position of r relative to c, or 0.75 meters in the I hat direction. And what we come up with is about 2.6 meters per second in the j hat direction. Now we need to evaluate the second cross product. So we take that, evaluate this term, the two terms. We're just going to cross 2.6 in the j hat direction with 3.5 radians per second, omega again, in the k direction. We'll come up with, for this double cross product, a final value of about negative 9 meters per second squared in the I hat direction. So the acceleration in the r direction is simply a negative 6.75 minus 9.19, or a final value of negative 16 meters per second squared in the I hat direction. So what I want you to try is to work this problem not with the axes set up here, but with the other case in which I worked in class, in which the blue axes are located at point O, and the blue axes they simply rotate with point C. So in that case, you'll come up with the same answers, but you'll cross off a couple of different terms. But if you're doing it right, you ought to come up with about 7 meters per second in the j hat direction for the initial velocity, and negative 16 meters per second squared in the I hat direction for the acceleration.